Hello everyone. We are going to start with the second lecture of Basics of Chemistry Part 2. So in the previous lecture we discussed about basics of atom. We discussed about atomic number, mass number, subatomic particles, mass of one proton, electron, neutron, and then we discussed partly about electronic configuration according to Bohr-Buie scheme. So I'm going to continue with the same. In the previous class, we discussed electronic configuration, like how much capacities those shells or orbits have in order to accommodate electrons. So there are certain elements which follow some stability rules. So these are dependent upon some noble gases. So we are going to understand about noble gases first. Then we'll move to the stability rules and how they are going to help us understand chemistry of 1 to 20 atomic number elements. So noble gases are group of gases which are chemically inert, or we can say stable. I'm again using the term generally because it's not true for all the noble gases. Now, in order to locate noble gases, what we can do, we can see the periodic table. If you can see, if you have it in front of you, I don't want to add a picture because you need to remember, you need to have a memory of the periodic table somewhat. If you always have periodic table in front of you, it's always, you'll be dependent upon that. So try to create an image in your brain. So if you see the periodic table, there are certain vertical columns. We call them as groups. So these are vertical columns. No doubt about this, we'll be discussing in the future lectures. So, in the 18th group, if we need to locate where it is, it's actually there in the periodic table, your left to the right side. So, left side is group 1 column, group 2, group 3, group 4, and if you go to the extreme right, so this is on the extreme right on the right of the periodic table. So I'm going to write in the same sequence. So under this 18th group, we have first element, that is helium, neon, argon, krypton, xenon, radon, and then we have the last element, that is organosin. So I'll write the names in the bracket. Helium, that's the first noble gas. Neon, argon, krypton, xenon, whatever you want to pronounce. Then we have radon, and then organism. Now, if we talk about these six noble gases, these all have, or even organism also, these all have 8 valence electrons, except helium. Helium has only K shell complete, that is atomic number 2. So these noble gases are generally stable. They are stable by nature. So I call them as a role model of the periodic table. So according to my imagination, and you can say according to the science also, the other elements, they try to imitate electronic configuration of these noble gases. Now this is true When it comes to your 1 to 20 atomic number elements, post that chemistry differs a lot. Even for certain elements in 1 to 20 atomic number, chemistry is very different. But on a general rule, we say, at least when we start studying chemistry, that these noble gases, if any element, after donating, losing, or sharing electrons, if it is having 8 electrons in its outermost shell, then it is considered stable. That's what stability rules I'll be writing now. So, helium has only K shell complete, that we need to remember. So, K shell complete meaning it has 2 electrons in the K shell. Apart from that, neon, argon, krypton, xenon, radon, or Gunnison, they all have 8 valence electrons. Now, I want to add one thing. Usually, I don't want students or anybody to get a shock in chemistry that to a certain grade we were saying this to this if we go to the higher grade then we have a different approach. Why is that? So I always believe in giving you some doses that this is what you're going to see different when you go to the higher class. So organism is a newly discovered element. We don't have any much literature whether it's a noble gas or not. So, if we talk about xenon, this definitely reacts with oxygen or fluorine under special conditions to form compounds like oxides, even oxyfluorides, like xenon xenon trioxide Xe2O3. This is one example I'm writing over here just to give an idea that even noble gases can react. So neon and argon, they are not having compounds. Krypton can make, your radon can also make, xenon definitely. So, where we are going to study this? We are going to study about these elements which are forming compounds somewhere in your P block chapter in your higher grades. So we'll be discussing in detail about the chemical reactions of noble gases, certain noble gases, not all, because what's the point of saying they are chemically inert if we do have exceptions, but chemistry is incomplete without exceptions, right? So this P block chapter is, you can say, we can't teach it in the entire, you can say, the whole chapter, but this P block actually start from group 13 and it ends at group 18. So, what is P over here? That again we'll be discussing later on, not right now. But there's always good to have a small doses of something linked in the higher classes, something linked in the more advanced chemistry, so that something is not alien when you're going to study it in natural. So, now moving ahead, according to these noble gases, we have something called as stability rules. So, stability rules are going to help us understand that why some elements are not completing their shells, but still they behave stable. So, it's because they try to attain noble gas configuration. So, these noble gases, at least what we are going to discuss in today's lecture, is about helium, is about neon, argon. We are not going to discuss about krypton, xenon, radon over here. So stability rules, we have something called as duplet rule. We have octet rule. So duplet rule, I always say that it is applicable for hydrogen only, the very first element. So how do you define it? So it's always better to know the concept, even if somebody is not going to ask. Duplet, dupe basically stands for two. That means two electrons in the K shell. So how we are going to write it? So if an element has 2 electron in its K shell, and it is the only shell present in that atom, of that atom in an of it in that atom of an element, then it is considered stable. After losing, gaining, or sharing electrons, as it imitates helium, noble gas, configuration. So if I am going to take hydrogen, atomic number 1, so 1 atomic number means it has only 1 electron in the K shell. So if this hydrogen can accept 1 electron from any other atom, it can change into anion, the negatively charged atom. So it is the only element. Just remember, hydrogen is the only element having 0 neutrons. So it was having 1 proton, 1 electron. Now it's having 1 proton and 2 electrons. So its K shell is complete. So it's imitating helium configuration. Now on a theoretical grounds, we can say we have lithium, atomic number 3. We have beryllium, atomic number 4. Now, in practical grounds, it's very difficult to remove 1 electron from lithium or 2 electrons from beryllium. We can do that. It's possible. It's not impossible. But they can show duplet, but it's very difficult to obtain. So that's why I never add these two elements, because ultimately they are going to show the bonding very differently. So hydrogen is the best example to understand duplet having K shell complete. So now next, coming to octet rule. Now remember what we are discussing over here. This is always going to be 1 to 20 atomic number. I'm not going to discuss anything apart from this. And sometimes there are some exceptions even in these atomic number elements between 1 to 20. So octet rule, from the term itself, oct, it stands for 8. So if an element has 8 electrons in its outermost shell, after gaining, losing, or sharing electrons from its outermost shell, then it is considered stable, as it imitates nearest noble gas configuration. So I can take example of sodium again. Atomic number is 11. So we have neon, atomic number 10. So out of 10 electrons, if K can accommodate 2, so leftover electrons out of 10 are going to be 8. 8 plus 2 is 10. So 8 electrons. So this is complete. If you remember from the previous class, L has the capacity to hold 8 electrons. So this is complete. So now we need to find an element. If we talk about sodium, sodium is 11 protons, 11 electrons, and if it is donating 1 electron and changing into cation, it has 11 protons and 10 electrons. So these 10 electrons over here also in neon also 10 electrons. So it's imitating neon configuration. So only by donating one electron. So we need to remember that elements cannot show nearest noble gas configuration on their own. They need another atom and they need a mutual benefit in that, either by donating electron, by accepting electron, or by sharing. When I use these three terms, donation, or we can use the term transfer, or if I'm using the term sharing, that indicates about the chemical bond that we'll be discussing in the future lectures. But just remember, alone atom cannot do or get stabilized on its own. It needs another element, another atom, in order to attain stability. And do remember, first we need to understand why these elements are behaving as an octet or duplet, because these noble gases are very much present in low energy system. Noble gases are highly stable and are present in low energy state or system, anything you can say. So elements are highly energetic. Now, they do have energy because they have electrons inside it, they have protons, neutrons. Now, when we talk about chemical reactions, we are dealing with electrons only. But what is holding these electrons inside an atom? Those are the protons. So indirectly all are participating, or you can say everything is important inside an atom, how protons are holding electrons and how the electrons is participating in chemical reaction. But the end goal over here is to attain low energy state. So wherever low energy state will be there, stability will be more. So moving ahead, before starting with 1 to 20 atomic number, chart, electronic configuration, etc., we need to understand about valency. So valency is something called as combining capacity of an atom, or it's a total number of electrons lost or gained or shared from the outermost shell during chemical reactions in order to attain stability or nearest noble gas configuration. So remember, valency can be zero, that is for noble gases because they are not chemically reacting, but with exceptions, definitely their valency or whatever charge those elements are going to attain, I'm talking about noble gases, that will vary. So it can be 0, 1, 2, 3, or 4. So these five numbers are always considered as valency. Apart from that, we always use the term plus minus charge. Now, I call it as a very simple generic term. We do have some concept of oxidation number. Again, we'll be studying in redox reactions. But just remember, it's a combining capacity. We are never going to put charge along with the valency. It's always going to be a whole number and always these five numbers. We never say 5 is a valency. We say plus 5, or you can say plus 3. That can be a charge, that can be oxidation number, we call it. But it's never going to be valency. Valency doesn't carry charge. So next is calculation of valency. Again, this whole thing is for 1 to 20 atomic number. So we can say for metals, we have valence electrons. Again, this is generally because there will be definitely exceptions. So valence electrons that we have are 1, either 1 valence electron, 2, 3 or 4. So I want to remove the 4, 3. Till 3 only we have. So valency for metals is going to be same number of valence electrons as metals tend to donate valence electrons in order to attain nearest noble gas configuration. So the idea over here for metals is they have less number of electrons. So metals have less number of electrons. So it's easier for an atom to donate less number of electrons as it is very much less energy expensive process that I would call. Then if we say about hydrogen. So hydrogen has only one electron in its case shell. So either it's going to donate, accept or share electron. So that is an exception. So over here I'm writing about metals. So hydrogen also has one valency, but it's not a metal. So we even call it as a controversial element because of certain similarities with metals and most of the similarities with non-metal. But typically we call hydrogen as a non-metal because it's a gas. It's a diatomic gas having two atoms in its one molecule. So then we go for non-metals. Again, I'm going to use the term generally. So valence electron for this, for non-metals in 1 to 20 atomic number is going to be 4, 5, 6 or 7. So how do we calculate valency for this? That will be 8 minus valence electrons. So 8 minus 4 is 4 valency. 8 minus 6 valence electron is 2 valency. 8 minus 7 valence electron is 1 valency. So I missed 5. So I'm going to erase it. 3 valency. 8 minus 6 is equal to 2 valency. 8 minus 7 is 1 valency. Now what about noble gases having 8 electrons in their outermost shell? So valency is 8 minus 8, that is 0 valency, that is for noble gas. Now exception over here, you can just remember, not for helium. Now helium is again a noble gas, but it has duplet. We say by default it has 0 valency, but we can't prove this with this formula, but it's a noble gas for sure. Now moving ahead, we are going to make a table. So we know atomic number, we know element, we know about electronic configuration now. So we are very much ready to understand this chart. We know about valence electrons, we know about valency, and we know about mass number, and we know about neutrons also. So atomic number is equal to proton number and it is also equal to number of electrons. Inside a neutral atom, we are talking only about neutral atoms. We are not talking about ions over here. Then we know electronic configuration starts from K, L, M, and N. We know valence electrons are the electrons present in the outermost shell. We know about valency, we just did a minute back. We know mass number is equal to number of neutrons plus protons. And we know how to calculate number of neutrons. You subtract protons from mass number, you will get the number of neutrons. So I'll write it over here. So we have A minus B that is equal to number of neutrons. So all these things are for your reference. See, all these things, it's very difficult to memorize, but with practice, you will attain greater heights. But if you know these very basics of chemistry, still it's not complete. There are multiple parts that I'll be uploading. But if you know this, your halfway problem in chemistry is done. So you can learn the higher levels of chemistry pretty easily if the base is strong. Remember, your base is going to hold the higher concepts. And if the base is not strong, you know, people can fall, buildings can fall. So, quickly starting without wasting time, we have our first atomic number, and that is our hydrogen. So it's H is a symbol. And do remember, I didn't mention about symbols. In chemistry, symbols, rulings come from IUPAC. You might have heard about IUPAC. If not, it's a association responsible for any kind of ruling in chemistry, International Union of Pure and Applied Chemistry. So if we talk about this IUPAC, why I'm introducing this part, because in the next video we'll be understanding it, the chemical formulas more. So why I was talking about this, because hydrogen, I wrote the symbol H. So it's just single alphabet. But in chemistry, if you have any symbol having two letters, the first letter is capital, the second letter is small. It's a rule. Again, I didn't write it. It's a rule. We have to follow rules. So hydrogen is a non-metal. Now from atomic number, we can see that it will have only one electron in its K shell. Valence electrons will be just one. Valency is also going to be one. Even it's a non-metal, we have to follow that concept. Mass is going to be one, mass number. So I'm not writing 1.008, which is mentioned in the periodic table. I'm writing mass numbers as whole, which is sum of neutrons and protons, and hydrogen is the only element having zero neutrons. Please remember that. That can be a very common question. In order to understand and remember it, you can see that mass is also one, atomic number is one, everything is one if you can see in this line, except number of neutrons, which are zero. Now, if you go to the second, that is helium, He. So these are two letters. So the first one capital, the second is small. So it's a noble gas. The very first noble gas, the lightest noble gas. Why lightest? Because its mass is very much low compared to the other noble gases in the periodic table. So helium has two electrons in the K shell. So K shell is only shell present inside in helium. So this is the only shell that we have. So automatically the valence electrons are going to be the same number. Valency is by default 0 because it's a noble gas. Now mass number is 4. Now how do I remember it? That's a tough part. So we have a trick that doesn't apply for all the elements in the period in this 1 to 20 atomic number. Again, you don't have to memorize masses for the whole 118 elements. It's not required, but 1 to 20 if you can, that will help you a lot. And it's always better if you can remember a few bits and pieces in chemistry. That gives you upper hand compared to other people. So in order to remember the masses, so 1 to 20, there's a small trick that I'm going to introduce over here. Hydrogen is easy to remember because mass is 1, atomic number is 1, 0 neutrons. End of story for hydrogen over there. Helium, if we talk about, helium has a double of atomic number. If you can see, the atomic number is 2, mass number is 4. That is double of atomic number. This is a learning trick. Please do not follow that this is any logic behind it. All these numbers are experimental, mass numbers are experimental, so there is no logic. So experimentally it has been found that helium has 2 electrons, 2 protons and 2 neutrons. So mass is 4. So this is just a learning trick, at least for 1 to 20 atomic number elements. So if we subtract 4 mass number minus the proton number, we will get how many neutrons? 2. So I'm just writing over here. So mass is mass minus proton is equal to number of neutrons. So 4 minus 2. So this atomic number is a proton number, mass number. So we will get 2 neutrons. Because in the next elements also I'm going to do the same thing. Now if you go to the next element, that is your lithium. So Li is a symbol, it's a metal. So it's 2 electrons in the K shell. I'm writing for your reference over here so that you can understand. And now out of 3 electrons, 2 will go into the K shell. Left over 1 electron will go into the L shell. 2 plus 1 is 3. So now this is our outermost. So we have 1 valence electron. It's a metal. And valency by default is 1, as I've discussed over here. If you go back, if you have 1, 2 and 3 valence electron, valency is the same number as that of valence electrons. So then we go to the mass number. Now lithium has a mass number of 7. So 7, how to relate it? How to remember this 7, lithium 7, how to relate it? So lithium atomic number is 3. So double of lithium 3 is 6 plus 1, that is 7. So double of atomic number plus 1 will give you the mass number of lithium 7. Now elements have multiple isotopes. Okay, lithium might have mass number of 8 or it can be 9. There can be multiple isotopes. Isotopes are basically elements with the same atomic number but different mass number. That I'll write it somewhere in between because we'll be dealing with mass numbers in this table also. But remember like this, if you have any other trick smarter than this, then please go ahead, do share with me that how to remember this one. I have one trick that I'm going to follow and I'm trying to share my knowledge with you. If you have better tricks, then please feel free to share. So 7 minus 3 is 4 neutrons. Then we go to the 4, that is your beryllium. Be is a symbol, so it's a metal. So 2 and 2 configuration. Now we are going to keep on adding electrons in the L shell. We have 2 electrons in the valence shell. We have valency again 2. Mass number for beryllium is 9, which is double of atomic number plus 1. 9 minus 4 will give you 5 neutrons. Then we go to 5, that is your boron. Now boron is considered as a typical non-metal. Because of its certain application, we call it as metalloid. So I'll write it as a non-metal. So 2 electrons again in the K shell. Now 3. Can you see? 1 we added, second, third. So valence electrons 3 again, same number. Valency is also going to be 3. Then we have 11 as a mass number of boron. Now some students in my offline classes, they say that odd numbers basically have double plus 1. Very excitingly they used to say that. And even numbers have just double of atomic number. It's not the case. If you see beryllium, we have taken 9, right? We can take different isotopes also. But these are the common mass numbers that we need to remember. So 11 minus 5 is 6 neutrons. Then we go to 6, which is carbon C, 2 and 4 configuration, 4 valence electron. Valency is 4. How do we calculate that? That is 8 minus 4. If we go back to this part, for valence electron 4, 5, 6 and 7, we subtract it from 8 and we get our valency 4 like this. So 4 valence electrons, valency is 4, carbon has a mass number of double the atomic number, that is 12. 12 minus 6 is 6 neutrons. Now we are going to introduce one concept over here. So we am going to introduce a concept of isotones. If you see, we have the same number over here, 6 neutrons. So iso in chemistry stands for same. So isotones are atoms having same number of neutrons. Do remember, they have everything different. If you compare boron and carbon, definitely they both are non-metal, we can add that. But they have chemical properties very different, and the only thing similarity that we have in between them is the number of neutrons. So how we are going to write the example of isotones over here? We can write like this. Boron atomic number is 5, mass is 11, and we have carbon 6. So how many neutrons are same in this case? 6. So I'll be adding some more examples over here. So we'll go to the next one, 7. That is your nitrogen. That is N is a symbol. It's a non-metal. So electronic configuration is going to be 2. So out of 7, 2 are going to be filled in K. 5 electrons are left. So we have valence electrons are 5. So valency is 8 minus valence electrons, that is 3. Mass number is 14. Then we have number of neutrons. 14 minus 7, 7 neutrons. Then we go to oxygen. So oxygen is a non-metal, it's a gas. So 2 and 6 configuration, 6 plus 2 is 8. 6 valence electron, valency 8 minus 6, that is 2. Then we have 16, double of atomic number, mass. So that is 8 neutrons. Then we go to 9, that is fluorine. It's a non-metal, 2 and 7 configuration, 7 valence electrons. Valency is 1, 8 minus 7. Mass is double of atomic number plus 1, so that will be 19. 9 plus 9 is 18, plus 1, 19. So 19 minus 9 is 10 neutrons. Then if we go to 10, that is neon. It's a noble gas, second noble gas. So 2 and 8 configuration. Valence electron will be same, 8, and valency is going to be 0 because it's a noble gas. Mass is double of atomic number, 20, and we have 10 neutrons, 20 minus 10. So we are going to write again one more example of isotones, that is fluorine, 9 and 19 mass number, and we have neon atomic number 10, mass number 20. So we are going to write 10 neutrons in the bracket so that we can remember it. So I'll stop over here for this lecture. It has been long enough. Usually I don't want to burden students more than half an hour, but anyways, so we'll continue from atomic number 11 in the next lecture of our basics of chemistry course. So till that, keep learning, keep revising, make a chart of this, paste it somewhere on your table, not on like in front of your table where you can see it every day. It needs to go in your long-term memory. So 5 minutes, you can revise, you can see it, so that whenever you're going to start this chemistry, it will stay in your mind because it will help you a lot. So till that time, thank you for learning with me. Thank you.